Important announcement. We've officially launched the structural trivia page.
Finally, a place to prove I know the difference between a drag strut and a collector.
You got that wrong yesterday. Come on.
It was a test yesterday for the interns. Anyway, there's a question on lateral systems, many questions, load path, steel, wood, even those little code clauses that haunt your dreams.
It's perfect if you're brushing up for your PE or mentoring, or you just want to flex on your coworkers during lunch.
And we're dropping new questions all the time. So if you ace it today, don't get cocky, come back next week and defend your title.
It's live now at theengineeringpodcast.com. Now go play, go brag, and go suffer.
All right, back to the episode.
The Structural Engineering Podcast.
Wow, we're live on the internet.
Live. Well, welcome to the Structural Engineering Podcast.
Yes.
What are we talking about today?
So, Max, I wanted to talk about kind of cool lateral systems, specifically for seismic. What's some more exotic systems that we don't get to use much or aren't used much? And then what are maybe a system or two that's coming up that is pretty cool, maybe makes sense, maybe doesn't, kind of thing?
And that is definitely where any research is happening. Like, we don't need to know a new system specifically for wind. Well, specifically for light forces, there's not that much tension there. But severe things, like an earthquake, really needs the best we can do.
Yeah, something I've always thought was really interesting about earthquake loading, I'm curious your thoughts on this, is like, it's very rare that a whole building is taken down from a wind event. Maybe a tornado or a hurricane, maybe a hurricane, Lamborghini, just takes that thing down. But, earthquake is such a dynamic force that's somewhat unknown with a system that is hopefully fairly well detailed to make it work. But I always find it interesting that, like, our wind, we keep changing a lot, and more than likely the components and cladding side of wind is the more important, truly, piece, because pieces of buildings fail from wind. But
yeah, an element fails. It's not the building falling down.
Yeah, and it's happened. It's not common, right?
Well, Zach, you're right, and you'll hear this part later. Wind damage is so unusual in the U.S. and seemingly everywhere with engineers and the internet that I can't find any statistic to a building maybe falling over. But wind also pushes on trees, and the tree wasn't properly engineered and it falls on a house. There are a lot of numbers for that. Minnesota, you have the highest annual loss from wind events, totaling $112 million.
As much as like an earthquake comes through and it just creates havoc. And so I think there's opportunity to do better and things like that. But I think before we even get into that, it's just talking about seismic in general. And really your passion about it, Max.
Oh, okay. I do like it. I don't like when it occurs, I suppose, but I do like to design for it.
Yeah. Why do you like to design for it?
Because it's intricate. It's just a little more detailed than most of our designs. And we don't look at the cyclic components of this from a day-to-day standpoint. When you design a building for earthquakes, you do not consider as the building shakes back and forth, these are built into the systems that we have. But just knowing that these exist and where you need to put strength to connections adds the level of complexity that I really like.
Yeah. Yeah, I'm right there with you. I think, a building that's governed by wind and in a low seismic region where you don't have to necessarily detail for seismic is a little more straightforward. And there's complexities. And, I think something too here that we're not, to be open with is we're not talking about tall buildings, right? They're all mostly governed, if not always governed by wind.
Yeah.
So there's some really cool systems. Some of these systems are even used for wind. But we're talking more the perspective of seismic today. So,
and I actually wonder, and I'm going to run a little calc, and I'll snip it in here. But at what point in a seismic design category D, kind of typical values, does wind start to control? Because I did the 10, 11 story in Utah, and that was still seismic, but Utah is pretty strong. And I don't remember if it was right on the edge. And anything taller, I was not involved.
Do you remember the wind speed in Salt Lake?
No, I think 125, but I don't remember. Of course I did this. I had to know. So let's say we have a 100-foot by 100-foot building, and the uniform weight is 80 psf. The floors are 10 feet tall, That's short, but makes math easy. The building period is less than the long period, which will cap our CS value at SD1 over period multiplied by R. And finally, building period is proportional to 0.02 times the height, typical shear wall number. And then wind speed is 22.5 psf, increasing each floor by a decreasing number inversely proportional to the height. Thank you, Excel. And bam, this fake building is seismic controlled up to story 5, up to 5 stories tall, and then it's all wind. Clearly, these are fake numbers, but it does paint a picture. The picture says, wow, this is complicated. It must be Picasso.
I want to think that like most of the places I've designed high seismic in have not also been high wind. I can think I can think of coastal, the West Coast. There's some areas because you have that exposure factor of like D because you have all that
ocean in front of
ocean
you.
lead up in front of you where it kind of speeds up the wind a little bit, but even there it was still governed by seismic. So yeah, it would be interesting.
I'm gonna run a little quick calc, just make some generic building, 100 by 100 square, and see how tall it can get.
While you're running that calc, you should also run this idea. And I know we've talked about this before. This is still in my mind. I need you to solve this for me. I think it was about 5 or 6 years ago. My sister.
Wow, this has been on your mind a while.
It's still been on my mind. And her husband were in Japan. She was texting me late at night here.
Wind event?
Earthquake and huge wind event. And she was saying the whole building was moving. And I think it'd be so interesting to think through and do a little bit of calculation of what the building is doing during both occurrences. I know we've had ideas in the past, but in Japan, it's something that's really common. I mean, right? They don't.
Yeah.
Their buildings don't really yield. Like earthquakes happen so much. They're really good at dissipating energy and kind of recentering or working for the most part or remaining occupied. But what happens also while you have a high wind event during an earthquake? Like how exciting as an structural engineer.
Yeah. Sure.
So Nelson Forensics has an article about this, but it's not really a blurb. The article takeaway was, the forces are high, things can fall down. But this is clearly so related to the frequency of the structure, the wind timing and direction, and the overlap of these things. But from a U.S. design standpoint, seismic forces are resolved typically by yielding in members. Wind is elastic response. Both of those together make a yielding response higher than the design intent. But luckily we have statistics, and that would tell us not to worry about it.
So to start off this conversation, I wanted to talk about the basics of seismic design, just a little bit to bring everyone up kind of to speed, whether you're in school or you just graduated, you're starting your career, or even if you're really experienced but maybe don't do a lot of seismic design. So kind of just thinking about seismic resistance, refers to a building's ability to withstand the forces generated by an earthquake without collapsing or suffering major damage. You can get into performance-based seismic design where you set performance values or levels, and that's something in seismic retrofit, so ASC 41, that you do that as well. But the idea of majority of our buildings, or category 2 buildings, is that you will survive the shake, you'll get out of the building, and then you'll have to do either major renovations or completely rebuild the structure. That's something I find very interesting that most of the public doesn't understand, is because the building has seismic resistance doesn't mean that it will be able to maintain its use after an event. It actually was many years into my engineering career that I actually learned that, which is really interesting. And I found, as you get to those higher risk categories, hospitals, police stations, fire stations, and then you kind of start trickling into that world of performance-based design, there is that importance of we need to keep this in place.
Yeah. I've found finding using AC 41 that actually leads just normal design a little more performance-based, and the amount I've dove into that is not that much. I think you've done probably more than I have, but it just gives you a good mindset of what performance you expect to occur after the design event. And it's not like the building is just fine. It is the people are hopefully fine. You design for immediate occupancy is definitely different than collapse prevention.
Right. It's a very interesting approach to take. I think it's really cool as a structural engineer to be able to make those educated decisions based off of a performance rather than a risk category. There's the perceived, with the importance value with seismic at 1.25 and 1.5 increases of loads, you understand that the building can see more, of course, but how do you communicate the perceived damage from an event where in ASC 41 or performance-based design, you kind of get to have that conversation in a little bit better way. You look at what would fail and how you'd solve it rather than the whole system all at once, which I think is pretty cool.
Yeah, and I know this is not a conversation about ASC 41, but just thinking of like, we take 2/3 of the maximum Earth acceleration, right, to get to an SDS value. We take an SS and chop that down, and then we know the building is going to yield like crazy. Our R value is a yielding reduction, essentially, that deformation is going to occur, but if we choose the right system, it can ride through this, and like we just scale down the force and still design a correct building. But ASC 41, it's like opening the hood to like what is actually what you're aiming for, what is going to occur, and I enjoy those projects.
So to continue on, the story here is earthquakes produce ground motions that push and pull structures in multiple directions. A well-designed building absorbs, redirects, and resists these forces to protect lives and property. Seismic resistance isn't just about surviving the quake. It's about minimizing damage, preserving function, and speeding recovery. One thing I want to note too that I found was very interesting is the earthquakes that occurred in I think the last big one that occurred up in Alaska. And they found that the buildings performed, I think, fairly well. But something that didn't was, and I remember this specific story of a school, was that the brick veneer did not, and it failed off the building and blocked the exit ways.
Oh,
so I think there's still, even in the seismic world, just like we talked about in wind, the components and cladding, I think the components part of a building, not just the facade, especially a heavy facade, should be engineered, but thinking through the ceiling and the ductwork and the piping, like in these regions, which are required to be done, I think it's really important to make sure that there's still that life safety. Maybe the building doesn't collapse, but what if a big water line, falls down? That's equally a big problem.
Yeah, gosh, that's true.
So Max, how would you say a building resists an earthquake? Let me even rephrase this. Okay, how do us engineers, what type of strategies do we have that allow us to resist those earthquake loads?
I mean, we look at it entirely elastic. We know the ground acceleration, and we reduce that a little bit, as I was already complaining about. Not complaining, commenting on. And we apply that load through the walls, up to the diaphragm, down to the lateral force resisting system. And we make sure that the building mass that is getting moved, so acceleration is put on that, what force is transferring through the diaphragm to the brace system, and we basically carry it in an elastic way.
So how would you put that if you had one word to choose? What is the most important thing that is used that we have to really think about, and what material is really good at this?
I would say ductility is the number one, and steel is really great. And honestly, most other systems we look at, like a wood shear wall, has a pretty high R value. The nail slipping is like, so everything is what yielding can occur and keep this structure stable. And steel is great at that.
And if you think about every single system, it is only steel that does this, right? Think about concrete moment frames.
Rebar. Yeah,
it's the rebar.
It's always
masonry. It's the rebar.
Yeah.
And when you get to unreinforced systems, our value is almost 1, right?
Yeah.
So ductility is really the thing we can use. It can flex and it can absorb. The other things out of my list here was redundancy. We have multiple load paths to ensure that if one part fails, others can carry the load. And there's, a redundancy factor that we use based on that. The more load paths there are, the better. Stopping on load paths, something I learned way early in my career that I thought was the most important thing or something that's really sat with me, maybe not the most, is how important a load path is. It doesn't have to be the right load path, and it doesn't have to be the only load path, but it has to be a well-detailed load path. Whether load will initially go there or not, you at least have the opportunity for load to get there. And I think that's like an interesting thing within engineering is like there's not always one load path, but you pick one, you tell it well, load will eventually get there, maybe a little more deformation than you expect. Luckily, with most of the seismic systems that we deal with, there's a pretty obvious load path, especially with the more common buildings.
And I want to add one element. I mean, you've talked around this, but redundancy and overstrength are both really I would say, fun elements in seismic design, because they kind of show you how you move the force through the building and then down into the resisting system, right? So like it takes a certain seismic design category to require redundancy, and it's not every system. There's a lot of complications there, right? But that with your overstrength is making sure you can get this force through a collector, through a core, like down to the resisting system with no yielding on the way, right? All the yielding is going to be the steel, as you said, in the lateral resisting system.
The other piece to this, continuing the conversation of strategies is your stiffness. That is a really important thing within seismic design, because if you go too far, and this is a big moment frame thing, there are so many second order things occurring as this building is wanting to fall over more or less. So preventing excessive swaying is a huge piece. It's not something let's talk mid-rise and below, not something you really run into too much with shear walls and brace frames, but moment frames, big deal.
Yeah, they're super flexible, and pretty sure in high seismic design category, we even have additional requirement on limit on our drift capability, right?
Right.
Is that 1.3
sure.
less? What is that? 0.7? I'll do 0.75 amount.
0.77.
And then divided by 1.3.
I think another important thing to always remember, and having some complexity in your design can be fun, but having a system that's symmetric and regular kind of keeps the forces balanced, and the design performs better, right?
Yeah.
The less irregularities we have, vertical and horizontal, our designs act better. All those irregularities were things they found from failures. These are bad things, and you have huge hits if you actually do it. You do use those. Sometimes you have to, but I think it's really important to always think through, like, the simplest design is going to always be the best. We can add the complexity into it, but I think making sure we're always pushing for simplicity is important, because we know it will perform because of how past things work. The code allows a lot of different things: vertical, horizontal, symmetric. Not to be symmetric, all those things. But when you can make it more balanced system, I think is better. A couple other pieces here, just at the end, strategies: energy dissipation devices like dampers that we're going to talk about. And then also base isolation, like what a cheat code right there. Let's just this is isolate the whole building from the ground and deal with very minimal movement and system. So from that, Max, what would you say are the three main lateral systems that we use as structural engineers?
I mean, our baseline is moment frame, brace frame, shear wall, right? The standards that we see.
And how would you say those perform differently? How do those act? When would you use one versus the other? We have an episode where you and I argue moment frame versus brace frame. So anyone listening that wants to hear Zach win,
I don't know.
Go right to that.
I don't know how to broadly categorize how they all act differently. And I'm thinking about them in a yielding sense, right? Moment frame is a reduced beam section, is a common one we use in the seismic area. And the edges of our beam that see the highest moment actually yield a little bit to create this fixed connection that can move a little bit more and dissipate some energy. Right? A shear wall, the thing is taking some damage to yield, but it's staying stable. It's reinforced to do so. Brace frame can be many options, right? A BRB system is great at yielding. The concrete core around our yielding steel member is keeping it contained. Like, that's a wonderful system. How they act just elastic forces without yielding. I'd say all kind of similar. A shear wall blocks a window more, and moment frame is the win.
What would you say, just for anyone that's on or listening to this, for each one of those, where would you typically see them? What's like? My mind goes to like moment frames are maybe more expensive, so maybe they're used a little less. And where might you use kind of each system? Yeah,
you're absolutely right on the cost. So moment frames, when windows are a priority, moment frames are kind of the only way to go. And you'll often see that at the perimeter of a building with a lot of windows. If you can get away with just a core system, that's shear wall in the middle of the building, or stair towers on each side of a building, they're taking most of the load. That's basically what I've done. Is in a core system, shear walls for taller buildings. That's what it is. In a healthcare setting or a taller commercial building, I've done a lot of cores or BRBs at the center, and then moment frames around the perimeter for torsional reasons. But that's a lean on our BRB. Our brace system is those can kind of go either way. They still block windows. They also look very nice. So if you could put them just right in the window, put a window around them, that sounds great to me. If any architect is listening.
Yeah, one might call that architecturally exposed brace frames.
Okay. Yes, that's smart of them. Yeah, so I think brace frames walk the line, core style systems or exterior. They can be wherever. And they can dodge windows, right? If you're not a high seismic design category, you can put eccentric brace, no problem, without weird calcs to make this happen. You can just put a diagonal brace that misses a window.
So I think that's perfect. That's a good little intro to the conversation we're going to have today. So to start us off, Max, you want to talk a little bit about why new systems are needed and why people are inventing new seismic resisting systems.
Yeah, I think there's just a general need to have the best system that we can come up with in a seismic sense. There will continue to be earthquakes. We are not perfect yet. There's a lot of, with this high R values, there's a lot of damage to a building. And there are systems like the base isolation where we just keep reducing that acceleration the building has to see, the forces that need to go through it, and maybe we're not breaking every non-structural wall in the building to make this happen, and it's not, we're just walking out alive, and that's wonderful. It's a little more advanced, and we have room to grow there.
So the first system I want to talk about is a self-centering system. This is something that has been used for, I guess, quite a while. There's rocking precast walls. Now there's a system called Tectonis that attaches to even your CLT shear walls and makes them kind of rocking, but allows it to recenter the building, because that's a huge failure mechanism over, post earthquake, as the building has more or less racked over and can't be recentered.
This is one of my favorite ones from a visuals perspective. I mean, Tectonis CLT combination is beautiful.
It's really cool. Yeah, for sure. So I wanted to add it as one of the more exotic systems. It's not used a lot. There is options to put this self-centering system in a bunch of different applications. So a few of the things I wanted to touch on, and for you listening, you should go look into these systems because they're pretty cool. There's minimal residual drift. So after an earthquake, buildings are often leaning or shifting permanently. This recentering system, like we talked about, uses more of a post-tensioning or special joints to pull the structure back upright, reducing the long-term deformation, which is often the reason that a building has to be, demoed or severe, really intense repairs are done. A reduced in repair costs, kind of like as we've mentioned. It improves the resilience. So an episode we had a long time ago, talking about the resilience of infrastructure. And I think it is something that's really important when it comes to the high seismic regions. Think about Katrina and the $100+ billion that was lost, or was, the economic impact of that per se. And think about the West Coast and a huge earthquake hitting Seattle, LA, any of these big towns.
Yeah, it was the New Zealand quake. It was Cleveland? Christchurch. The New Zealand quake, Christchurch, right? That wrecked the entire town.
Yeah. So think about the economic impact. I mean, the impact to life, first and foremost, was devastating. But as you get into resiliency of your whole system, what does that look like? How do you appropriately put money in those areas to not, to make sure that you're resilient with time? So this is a system that, as it can be recentering, is critical for infrastructure like hospitals, emergency centers. Think for more of our higher category items. It enhances the safety, reduces our collapse risk. As we're talking, through performance categories, it really is beneficial. Sustainability and longevity. You don't have to repair as much of the building or tear it down completely because the system recenters itself. And then design flexibility. It can be integrated into concrete, steel, masonry, timber systems, as you're saying. And it's compatible with kind of all different types of construction. So I just wanted to hit on that. Self-centering systems, I think we're going to see a lot more of, especially in the mass timber world. Yeah. This is, in my mind, like one of the big places to use it, because it really fits well with the capacity of CLT panels.
Yeah, CLT panels can be very stiff. They themselves are not great at yielding, but if you combine this with the self-centering, that's perfect.
So Max, a system that's been used quite a bit in some really cool case studies is base isolation. What are your thoughts on that? What's the benefit? I mean, I put it into the exotic category because it's not used a lot. The day-to-day engineer has never designed a base isolated system similar to self-centering system.
Yeah. I mean, my general thoughts, of course, it's an amazing system. I say this again, but it reduces the force dramatically that the building has to see, right? It's almost seeing just wind force. It's pretty complicated, and it's complicated from the math standpoint, yes, but also you have to allow this building to shift, whatever the answer is, but 8, 10, 12 inches. And so the stairs leading up to the building, there needs to be a gap. So you see these expansion joints in a parking garage. Like many buildings, you see this, but those are 2 inches. You're talking a massive gap, and so there are ways to do this, but it just gets pretty complicated. You're putting this building in essentially a pool that it's swimming in. So complicated and fun.
Yeah, the Structure Mag articles I've seen of where they've come in and added base isolation is so cool. They shore up the building, they build that basement below, some concrete columns up with the pad. I always think it's fascinating when they take the load off the foundation or anything that's heavily loaded and put it onto something else for a permanent, and the building remains stable. I mean, how cool.
I lived in Utah for a while and did a lot of seismic there, and the probably best presentation I've ever seen in general, but base isolation, is the Mormon Temple in downtown Utah. I don't know if it's completely done now, but they base isolated it, and it's a 150, I'm guessing here, of course, masonry building that is not great at yielding, and they picked this thing up and put it on base isolators that are pretty complicated. It is the most amazing system I've ever seen. So really, you should Google this, and there's some great slides and pictures that are worth checking out.
The next one I wanted to talk to you, Max, about, and this is, I think it's really cool. Early on in our podcasting career, we did an episode with Taylor Devices about a viscous damper, and that changed everything. They talked about that their dampers on so many more things than just buildings. It's on bridges. It's on the International Space Station. The aerospace world uses it, and it's so cool. And the best, the way I think about this often is just a car, right? Like how a car rides along the road and deals with the bumps.
Yeah, I think of it in a similar aspect. Is what if you take the shocks out of your car once? It'd be absurd. No one would drive a car without shocks, but dampers on a building, that seems so exotic. And they're kind of the same idea, and it'd be interesting to explore this more and maybe be a more common system.
So I want to just read an explanation of what a viscous damper is for anyone that doesn't know, and I think it does a really good job of explaining kind of how it works. If you want to see a schematic of how one kind of works, you should just Google viscous damper.
And I'll throw in the show notes as well.
So in viscous dampers, seismic energy is absorbed by silicone-based fluid passing between a piston cylinder arrangement. Viscous dampers are used in high-rise buildings in seismic areas. We've also found that they're used in maybe mid-rise buildings or in seismic retrofit situations. It can operate over an ambient temperature range from 40 degrees C to 70 degrees C, and the viscous damper reduces the vibrations induced by both strong winds and earthquakes. So it is really a schematic of the shock absorber that is on your car. It's just this piston that is attached at both ends. A lot of the ways you see it installed is in line with a brace frame. And if you wanted to learn more about this specific type of viscous damper, listen to our Taylor Devices episode. Max will also throw that in the show notes, and maybe throw it in right here what the episode number is.
I don't know why they were willing to join us so early, but this is episode 14, Structural Dampers featuring Taylor Devices. 2019.
So Max, another pretty common system when we're talking about using a damper would be a viscoelastic damper. What do you think about those?
I think they're very cool, believe it or not. You might expect me to say. So that, right, takes the force applied to this building and shakes it, slows the building down, essentially transfers the motion of the building to heat of this system and dissipates that heat. So you're like a shock and a spring. We kept kind of generically saying a shock, but those are different items. The car springs are what keeps it moving. Shocks are what slows it down. A shock is essentially a viscoelastic damper. Kind of. There's less damage going on, but you're giving your building a shock to slow down its force, which is just another really cool system. Yeah, I would love to see these more, of course, as well.
So a friction damper, which is, let's say, the third more or less used device, is really exactly what it sounds like. There's steel plates that are allowed to slip together, and as things move, that friction builds up, and the heat is what helps dissipate. So a friction damper device consists of several steel plates sliding against each other in opposite directions. The steel plates are separated by shims or a friction pad material.
And I want to say quickly, like friction damper and a viscoelastic, right? This is something that is moving, that's creating heat. That's kind of the only way we have to dump energy out of a system. And so they're kind of similar. They just have a different mechanism to get there.
Right. The damper dissipates energy by means of friction between the surface, which are rubbing against each other. It's also possible to manufacture surfaces from materials other than steel. I think the geometry of how these work, they kind of look funky or even fake. You're like, why is this connection overly complicated? But that, like, if you saw this in nature, you'd be like, man, was someone doing some art with some brace frame connections? But it truly is art, thinking through like how they dissipate the energy and the system behind that.
Yeah. So, and there's a lot of systems, a lot of research going on here. So there are many systems that perform like this.
So one that we have talked about on the podcast and fairly recently is a tune mass damper, when we talked about Taipei 101 with the engineering firm that designed that. So Max, you want to go into a little bit of a tuned mass damper? I always say it backwards, and how those work.
I will try, but I'm not sure that I can do a perfect job. And I've described this to friends. So when a building moves, right, if you have a large mass essentially on a pendulum that's maybe the same period or derivative of the period of the building, it will kind of stay in place for a second, and as the building wants to move back, they'll be opposing each other, right? And so the movement of that mass, if you control it a little bit and resist the movement, you're essentially pushing back on the building. So if you build this system, so the building has to move quite a bit the first time, not quite a bit in a bad sense. Building moves, the tune mass damper stays put, and then the building moves back. Now they're out of sequence of each other. The tune mass damper wants to push the other way, and if you have some resistance to its swing back, it'll halt some movement, and it could really slow down the acceleration that people feel in a building. You don't want to use a TMD to make sure a building doesn't fall down. You don't want to push it to that extreme, but comfort, absolutely, and it can do a great job.
The other one I think is pretty cool is the yielding damper. This one's a little bit of a hard one to fully explain, but think of it this way. You have a steel plate at the top, a steel plate at the bottom, and you have these like little fins that run vertically, and they're in such a shape as the two steel plates oppose each other in direction, that you start getting a little bit of energy dissipation from all of these little fins. If that doesn't make any sense to you,
it doesn't.
And it doesn't even make sense to Max, as he's giving me the weirdest look right now, and he's seeing the same picture I am. Go Google yielding dampers, and probably Max is about to say, and I'm going to beat him to it. It'll be also in the show notes with this. But there's some really cool systems like this. One thing I think with some of these, and this one specifically, is how much are they used? How many, are they more used in new buildings, retrofits, and what is the basis of success behind an actual event? Like Max said, a lot of these are kind of still in research and stuff. So I think as you're looking into these, if you're seriously looking into these, I think obviously go way further than this podcast. There's just an entry of how this works. So, or the different options really. And the last one here that I want to throw out to Max is a magnetic damper. I have no clue if this is actually ever used, but this is something I found that was really cool.
In the show notes in the document that we're looking at that describes magnetic damper, there's a power cord. If this is an electronic magnet, that's a bad idea. Is it?
When I saw this, the thought I had was, is this damper there for human comfort or for seismic performance?
Yeah,
because that's something we didn't touch on either, is a lot of these tall buildings have these types of systems to lower that that acceleration of movement for human comfort just in the building, not during any type of, a seismic, high-end seismic event, but just for like the wind.
TMD, right? Type A 101. It's there for comfort. All right. It's acceleration of the building, reducing that. It's pretty windy in Type A. And
that was one of the cool things when we learned about that they told us is like the building, when you have a system with a damper, the building still has to perform without it, because all of these things could fail without more or less maintenance done to them. It's something that has to be continuously maintained to some extent. A viscous damper should have a very long shelf life, but it's something, if you go into the building and one of the seals have failed, you can't have a building that no longer works just because of that. So these systems specifically have maintenance to them. And even Type A 101 has viscous dampers involved in it, and those are things that have to be maintained. It's not necessarily just a standalone, just big mass being hung. There's still those viscous dampers on, attached to the bottom of them. If you were to see a picture of Type A 101,
essentially shocks, right? They're transferring the force slowly to the building.
So when I think about the exotic systems and like the things we'll see being used way more often, these are them. The viscous damper, base isolation, and recentering systems. I think there's some other cool things BRBs are awesome. I think a lot of the systems are going to be used less because of BRBs. They're cost effective. You can replace them fairly easily. You can have a bolted connection. So those are, that's already in the code. These things are beyond, these are moving beyond what ASC 7, chapter 12 allows us to utilize. I guess there is some base isolation in ASC 7, but from when we get into viscous dampers as well as self-centering systems, we're going a little beyond the code.
Yeah, and there is a little competition to the BRBs, and I agree. It's an amazing system. Tectonus, though, recently has put out some great systems that are very similar, so it's going to be competition. Their website says straight swap for BRBs, and it's basically a damping and yielding system. It doesn't have an R value yet.
Whoa, yes it does, sorry. R of 8, it's a straight swap for a BRB, high damping, 50%, low overstrength of 1.15. It's a pretty nice system.
But it has very similar components to a BRB. Still a diagonal brace, but it can suck up the energy that the building is seeing.
So Max, before we move on to this last system that I'm really excited for you to describe, what other systems have you seen implemented out in the world, a Structure Mag article, something in a white paper, some research that's done that has excited you or think that would be good to have the listeners know?
This is not directly answering your question, but thinking of a Structure Mag article, there was 3 months ago a efficiency and size and design article, and I really like that you can these ideas are one and the same, that an efficient building is designed well, as we were talking about, like damage that a building sees. If your seismic system reduces the damage to a building, you're not constructing the building again, you're saving quite a bit. That was an article, and it will be a webinar in 3 months, I think.
From 3 months from when, Max?
Oh yeah, it's middle of July.
I'll just link this article. It was pretty good, and I think the webinar is going to be great.
Yeah, the other cool system that is codified now is the speed core that they use on the Rainier Square building. I think that's been implemented a few more times.
I'm not aware. I'm sure it has, but I'm not aware of a time.
So Max, beyond the speed core, like what else do you think is a pretty cool system?
This also Structure Mag article that I can't quote verbatim here, but it was basically called a mast frame, and it was keeping a rigid building system so that after yielding occurs, the building is still performing to, if a second quake, you're still okay. But it allows the performance of a higher system. And I'm going to link this article. They're, I think, also going to do a webinar eventually. Who knows?
And we're going to have them on the podcast. We're going to try our best.
I'm going to try so hard.
Because the system also incorporates BRBs.
Yeah.
So it
combines, it is basically a braced frame system in combination with a yielding system. And they're kind of independent, but they work together in a great way. I don't know.
So depending on what podcasting platform you're listening to, it'd be great to throw a comment down there of what your favorite system is or what you think is cool and upcoming, as well as send it to us on, any of the social media platforms, or just email us. It'd be cool to hear. So the last system we would kind of want to just throw out there and have you guys do a little more research on, because it is still the research stance is a brace ductile shear panel system, or BDSP.
It's a combination of so many words. I mean, that sounds elaborate.
The way I can think of it best is it's a very unique hybrid mechanism. It's got, the benefits is it can control damage and be repaired. The best way to explain this is just a big X, and where the X occur, the intersection of the two braces in the center occurs, there's just a big rectangular steel shear panel that would intercept the braces. But there's no braces. This steel panel appears to go out to all the nodes. The nodes have these connections that have pins, round pins on them to allow rotation. But then through the shear zones out to those pins are cables. It is really fascinating. And we kind of just wanted to end the episode with that little, piece of tech for you to go look more into. So
I hope someone can understand this and explain it to me, because it looks like a combination of every possibility. Tension only items, cables, sheared, compression. I mean, it's every possibility. But if it works well, let me know.
Thanks for listening to this week's episode of the Structural Engineering Podcast. We hope you enjoyed learning about more exotic seismic systems, and we're excited to hear what other systems you think are pretty cool.
See you later.